time we were discussing ideals, and we came to the realization that the notion of ideal, the definition of ideal, is essentially cooked up so that we could create what we call the quotient ring, right? It is exactly what we need so that when we look at the set of cosets R mod I, right, the operations of both addition and a coset addition and coset multiplication are well defined, right? So essentially, R mod I, the set of cosets, is a ring under coset addition and multiplication if and only if I is an ideal. So we've got that now, right? This is what we call the quotient or factor ring. I always say quotient, but I think your book calls it a factor ring. And what I want to do is just look at some examples now. So as a first example, let's describe the cosets of R mod, not R, sorry, Z mod NZ. Right, so it's easy to see. In fact, we checked that NZ actually is an ideal of Z. And so a typical coset, or a typical coset is of the form, say, A plus NZ, where A is any integer. So if you like, this set of cosets right here, in fact, let me write it in set notation. So Z mod NZ, right, it's the set of cosets of the form A plus NZ, where A is any integer. That's not a very efficient description, though, right? And so what we need to do is remember, what does it mean for two cosets to be equal? Well, A plus NZ is equal to B plus NZ if and only if the difference A mod B, or A minus B, is an element of NZ. In other words, A minus B, their difference has to be a multiple of N. And so now we think, oh, okay, anytime if you take a coset, right, so if you take some coset of the form A plus NZ, it's going to be exactly equal to a coset where the coset representative lives between 0 and n minus 1, right? Every one of these has a difference, a multiple of n with somebody. So let's say it like this, let me write it out. A plus nz is equal to r plus nz, where who is this n, or who is this r? R is in the set 0, 1, up through n minus 1. And who is this r? It's exactly the remainder that you get when you run the division algorithm, divide n into a. Okay, fine. So what that tells us is, and I'm just kind of, maybe I'm getting a little scribbly here, but what I'm trying to do is get a more efficient description of this set of cosets, and here it is, right? Z mod nz is really equal to, or a better way to think of it is that it's going to be the set of cosets 0 plus nz, which we can write as nz, 1 plus nz, and we go dot, 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 all the way up to n minus 1 plus nz, right? Every single coset of this form is equal to one of the cosets on the list. So here's a good description of the cosets of Z mod nz. And that's kind of what I want to do is just get our hands dirty. We're going to look at various quotients and try to get a sense for who this quotient ring is, right? So our next example, let's work with polynomials. So in R bracket X, right, the ring of polynomials with real coefficients, I want to look at the ideal generated by the polynomial x squared plus 1. So remember, the ideal generated, let me write it off to the side, and you can put it in your notes wherever you like. But remember, anytime the ideal generated by little a is equal to the set of all things of the form r times a, where r runs through all of r. So in our case then, right, we're going to have the ideal generated by x squared plus 1, well, what that's going to be then is all things of the form g of x times x squared plus 1, where g of x is any polynomial in R bracket x. And so, oh, here's a good way to think of this. The ideal generated by x squared plus 1 is the set of all polynomials who have x squared plus 1 as a factor. Okay, so now what I'd like to do, I want to consider the quotient ring R bracket x mod x squared plus 1. And I just want to play around with a little bit and get a feel for you know, what do the elements look like? Who are the cosets? Let's try to describe somehow. I don't even have a good sense of what I should say here. Let's just try to figure out, who is this? Is it familiar? Is it completely weird? Who knows? So let's see what happens. So let's see, a typical element is of the form, so let's see, it would look like f of x plus ideal generated by x squared plus 1, right? So these are the cosets. What I want to do now, just like I did this example a second ago, right? And in the end, what did we do? We said, oh, every time if you have a coset like this, you can find a convenient coset representative by running the division algorithm on A, right? And so it would be equal to the remainder when you ran the division algorithm. So what I'd like to do is run the division algorithm on f of x. I'd like to divide x squared plus 1 into f of x. So by the division algorithm, f of x is equal to x squared plus 1 times g of x plus, I guess I usually use a q of x, so times q of x plus r of x, where both q of x and r of x are elements of f bracket x, and the degree of r of x is strictly less than the degree of x squared plus 1, which means that the degree of r of x is less than or equal to 1. So now, what does that tell us? So now, note that f of x minus r of x, so if you subtract, what you get is x squared plus 1 times q of x, and this is an element of the ideal generated by x squared plus 1, which means, so let's say it like this, it follows that the two cosets, so f of x plus ideal generated by x squared plus 1 is equal to coset r of x plus x squared plus 1. Why? Because their difference lives inside the ideal. Okay. So that means then that, yeah, we said typical elements look like this, but actually we have a convenient choice of coset representative. We can use a coset representative whose degree is less than or equal to 1, which means that all elements of this quotient are actually of the form a plus bx plus ideal generated by x squared plus 1. So we can say thus, every element of the quotient r bracket x mod I is of the form a plus, or how do I want it? Ax plus b? Yeah, I don't know, for some reason I did a plus bx, so let's just go with that. A plus bx plus ideal generated by x squared plus 1 for some a and b in R. And this is it. Every time you choose a different a and a b, you get a different coset, right? So we should say and this representation is unique. Meaning if I choose an a and a b and an a prime and a b prime, the cosets a plus bx plus ideal and the coset a prime plus b prime x plus ideal are not equal to each other. They are different elements within the quotient. All right, so in fact, let's write this out. Yeah, let me write out what I just said. So that is r bracket x mod ideal generated by x squared plus 1 is equal to the set a plus bx plus ideal generated by x squared plus 1 where a and b run through all of R, and a plus bx plus ideal equals, let's say, c plus dx plus ideal, if and only if a equals c and b equals d. Okay, so now we have a nice description of the elements of our quotient here. Let's now see how addition and multiplication behave. All right, so addition goes like this. If I do a plus bx plus the ideal plus, so let's put some brackets around here, I guess, c plus dx plus ideal, that's equal to, well, you just add the cosets. And so that's going to be a plus c plus b plus d x plus the ideal. Okay, so, nothing too exciting, right? What do? You add the constant coefficients, you add the degree 1 coefficients, that gives you the corresponding coset represented over here. So now let's look at multiplication. So if I do a plus bx plus ideal, multiply that by c plus dx plus ideal. Okay, so now I need to multiply the polynomial out. So this will be AC plus AD plus BC. So AD plus BC X. Did I get that right? Let's make sure. AD and BC, yeah. And then it's going to be BDX squared. plus our ideal. Oh, this is not a good answer though. Because remember a minute ago we said that we could write down each element of our quotient using a coset representative that was at most degree 1. And here I'm sitting here with a degree 2. So I need to replace this with the corresponding, you can think of it as running the division algorithm if you like, although we're going to be a little bit slicker about it. So let's say it like this. So note that x squared plus 1 plus, well, okay, yeah, okay, say 0. 0 equals, now let's say it like this. X squared plus 1 is equal to, right, it's the identity coset, is equal to x squared plus 1 plus ideal generated by x squared plus 1. And so, x squared, I'm going to bring the minus 1 over. So let's write it like this. Minus 1 plus ideal is equal to x squared plus 1. In other words, this coset and this coset are the same, which means I can replace my x squared right there, right, with a minus 1. So this is equal to, sorry, this was kind of scratch work. I should have done this a little bit better. I hate having such a tiny board. So this is equal to AC minus BD plus AD plus BCX plus, I just put a minus 1 there, and then I brought the constant coefficients together, plus the ideal x squared plus 1. And now, you're supposed to stare at this for a minute and say, okay, when we added, you added the constant stuff, you added the degree 1 stuff. When you multiplied, okay, so remember what we were multiplying. We did AC minus BD, and then we did the AD and the BC. Does this look familiar? Let me just leave this as a question. Look familiar? In particular, and this might be maybe a little bit better of a hint, can you think of anywhere where when you square something, you get negative 1? So we'll come back to this example in a little while. We need a little more technology before we can fully analyze it. But this really should look familiar to you, and I'm not going to tell you the answer. Okay, so the next result, so let's say theorem 26.5. Let's let, let's see, I need an ideal, so let's let I be an ideal of R, and oh no, so now new sentence. Okay, so then we had this similar results for group theory. So then the mapping say eta from R to R mod I, defined by eta of an element equals its corresponding coset, is a homomorphism with the kernel of eta equal to I. We proved almost all of this in Math 481. So for the proof, we proved from group, that it's a group theoretical homomorphism. So we proved homomorphism under plus, and we also know who the kernel is. Found kernel of phi, or not kernel phi, kernel of eta equal to I last quarter. So now we just need to check that it respects multiplication. And so now eta of, let's actually start a sentence here. So now eta of RS, that's pretty obvious how this is going to go. This is going to equal RS plus I, which we now know can be written as R plus I times S plus I. And so that's eta of R, eta of S. I'm going to do one more theorem, and this theorem should look familiar also. So theorem 26.6. And this theorem has a name, right? It's called the first isomorphism theorem. So now let's let phi from R to S be a homomorphism. Then R mod the kernel of phi is isomorphic to the image of phi. And we've proved most of this, right? In fact, yeah, so there's only one thing to do. So let's see, how do I want to say this? It's the same mapping, so let's define phi bar from R mod kernel of phi to phi of R by phi bar of a coset equal to the output of its coset representative. Now, last quarter, so in 481, remember? This is a group. That's a group. Everything here is groups under addition. And so the only part that we haven't proved is the part about multiplication. So in 481, we showed that phi bar is well defined, bijective, and is a homomorphism under addition. So now all we need to do is take a look at what happens under multiplication. So phi bar of R plus kernel of phi times, I guess, I don't know, R prime plus kernel of phi equals, let's put it over here, phi bar of r prime plus kernel phi. Which is equal to phi of r prime. But we know that phi is a homomorphism, right? So I can split this up. So that's phi of r prime. And now we can put it all back together. So that's phi bar of r plus kernel phi times phi bar of r prime plus kernel phi. Okay, so that's all we needed. One thing to say, it sucks having such a small board. I mean, to me, it's very important to do your equations, your inline equations correctly. So if I would have had more room, if I didn't have to keep erasing and so on, remember, this really should look like this, and then one piece here, and then equals, equals, equals. Line up your equal signs, make your proofs look nice with your equations. This is a little bit sloppy, and my excuse is I just don't have any room, right? But on a normal board, you know I would have done it correctly. So, this is a good place to stop. We'll do applications of first isomorphism in the next lecture. All right, so we see you then.